Many real engineering systems can be extremely complex, making signal analysis difficult and sometimes impossible. Fortunately, a large class of systems follows a simple mathematical behavior known as linearity. This property allows engineers to predict system responses, simplify calculations, and design communication systems efficiently. When signals pass through a system, predicting the output is not always straightforward. A small change in the input may sometimes produce a large change in the output, while combining two input signals can create unexpected results. Without a predictable relationship between input and output, system analysis quickly becomes complicated. In communication systems, engineers often need to understand how multiple signals interact within amplifiers, filters, and transmission channels. If every new input required a completely new analysis, designing practical RF systems would become extremely time-consuming and inefficient. The challenge is finding a class of systems whose behavior remains predictable regardless of the specific signals applied. This requirement leads to one of the most important concepts in signals and systems theory: linearity. A linear system is a system that satisfies two fundamental properties: superposition and scaling. Superposition means that the response to a sum of inputs equals the sum of the individual responses. Scaling means that multiplying an input by a constant results in the output being multiplied by the same constant. Together, these properties create a highly predictable relationship between input and output. Engineers can analyze simple signals individually and then combine the results to determine the behavior of more complex signals. This dramatically simplifies system analysis. Mathematically, if a system produces outputs y1t and y2t for inputs x1t and x2t, then a linear system must produce a corresponding combined output for any weighted combination of those inputs. Intuitively, a linear system behaves like a perfectly proportional machine. If one input produces a certain output, then doubling the input doubles the output. Similarly, if two inputs are applied together, the resulting output is simply the combination of the individual outputs. Nothing unexpected occurs. Physically, an ideal amplifier provides a useful example. If a 1-volt input produces a 1-0-volt output, then a 2-volt input should produce a 2-0-volt output. Likewise, two separate signals amplified individually should combine exactly the same way when amplified together. Mathematically, consider a system defined by yt equals 5xt. Multiplying the input by 2 automatically multiplies the output by 2. Adding two inputs together produces an output equal to the sum of the individual outputs, satisfying both linearity conditions. Linearity is critically important in RF engineering because many analytical techniques depend on it. Concepts such as convolution, impulse response, Fourier analysis, and frequency domain modeling all rely on systems behaving linearly. Without linearity, these powerful tools would lose much of their usefulness. In practical RF systems, filters are often designed to operate as linear systems so that different frequency components can be analyzed independently. Communication channels are also frequently approximated as linear systems to simplify signal propagation analysis. At the system level, linearity enables engineers to model complex communication systems using manageable mathematical frameworks. This makes it possible to design and optimize technologies such as Wi-Fi, LTE, 5G, radar, and satellite communication efficiently. Although linear systems are extremely useful, many real-world devices are only approximately linear. Components such as power amplifiers, mixers, and active semiconductor devices often become non-linear when operating at high signal levels or near their physical limits. A common mistake is assuming that every system encountered in engineering is linear. In practice, many systems behave linearly only within a limited operating range. Ignoring nonlinear effects can lead to inaccurate predictions and unexpected system behavior. The study of linear systems serves as the foundation for more advanced topics in signals and systems. Once linearity is understood, engineers can explore time invariance, impulse response, convolution, and Fourier methods that build directly upon this concept. In this lesson, we learned that a linear system satisfies the principles of scaling and superposition, making its behavior predictable and mathematically manageable. We also saw why linearity is essential for many of the analytical tools used in signal processing and RF engineering. In the next lesson, we will explore time invariance and learn how systems respond when signals are shifted in time. If you found this useful, like the video, subscribe, and follow for the next lesson.